Welcome to Breadboarding. In the previous video I covered the introduction to building the CGA video controller card, and we laid out the chips from the previous design on 7 breadboards, 5 across the top here and 2 down the bottom. Now I had some feedback from that video, and one of the commenters said please could do a very detailed and technical breakdown of the CRT graphics controller, sequencer, attribute controller and various clocks all work together please. And there was a couple of other comments following on from that just to clarify what it meant by that. So it's very rare that I've been asked to actually provide much more detailed technical information, but I aim to please. So what this video is going to do is go into a bit more detail of the CGA video controller and the Breadboard PC version, which we are making CGA compatible from a software viewpoint, but it will be producing VGA output. So this is part 2 of the Breadboard PC version 2 video 11. So this is just really going into more detail and going through more schematics and explaining how the various clock signals and latches and shift registers and things like that work. So it's worthwhile perhaps looking a little bit at where computer monitors came from. So the early computer monitors were really just televisions. It's worthwhile understanding some of the parameters involving TVs, in particular more colour TVs. Black and white TVs are very similar, just a bit simpler. The first colour TVs came out around in 1954 in the US, and the NTSC colour standard was based on 525 lines per frame, with only about 480 lines visible, so you can begin to see where some of the video resolutions for VGA come from. It was based on 60 frames per second because of the US mains frequency there. These frames were interlaced, so of the 525 lines, we'd only have half of those at a time, so that gives an effective frame rate of 30 frames per second. The horizontal line frequency is quite often specified with monitors, and in particular, you need to make sure that the monitor you use is compatible with the horizontal line frequency. If it isn't, then it could even damage some of the older cathode ray tube monitors. Generally, LCD monitors won't be damaged in the same way. And you'll also notice that there's a colour subcarrier frequency, and this only 3.579 megahertz now. The original IBM PC actually had a 14.3 megahertz crystal, and that is actually this frequency times 4, and it's used in some of the composite colour output in the CGA video card. And in fact, the original IBM PC runs at 4.77 megahertz, which is that 14.3 divided by 3. Now, the video bandwidth was only about 4.2 megahertz, and the reason why that's important is when we start to look at outputting pixels or dots to a display, then the video bandwidth there is not very great, and in particular when the early computers and the early PC even would use an RF modulator to take the video output and convert it into the frequencies necessary for the radio frequency input on a TV. Most TVs in those days wouldn't have had composite inputs, SCART video inputs and things like that. So the fact that a lot of early computers had to output video through this RF modulator restricted the resolution that they were able to run at. And the original TV standard had then been reissued as a digital standard, as generally known as 480i, or sometimes it will be known as 60i or 30p, referring to the vertical refresh rates. Now in Europe, colour televisions arrived about a decade later. The PAL standard was developed by a guy at Telefunken, a German TV company. There was also a CCAM standard from France, but I'm not going to go into that in great detail. It's a similar sort of number of lines and things. So the PAL standard was actually slightly higher resolution. So we had 625 lines per frame. That gave us 576 lines visible on the screen. But that was done at 50 frames per second. So that was closer to the main frequency in Europe, and because this was also interlaced, we effectively only got 25 full frames a second, so we would get 576 lines per 25 times a second. The horizontal line frequency is very similar, slightly different, and there was a different colour subcarrier frequency to just slightly higher resolution, and the PAL standard avoided some of the colour issues that the NTSC standard had. Video bandwidth was a little bit higher, so there was a little bit more scope for driving these monitors through an RF modulator. Teletext was an information service built into TVs from the sort of mid-70s onwards, And this actually allowed up to 40 characters across the screen, 25 lines down. And in fact, this was actually running at a horizontal resolution of 480 dots and 500 lines. So it was using a 12 by 20 pixel. And because the characters didn't have to go through an RF modulator, then this was actually provided quite a stable text. It would be difficult to do this level of text through an RF modulator. BBC Micro did actually have this output, but the text clarity wouldn't have been quite as clear as a built-in teletext. And this was then replaced by a digital standard 576i, and also sometimes known as 50i or 25p, referring to the vertical refresh rate. But you can see the 576i refers to the number of visible lines. So some of this legacy cathode ray tube stuff still lives with us with the standards, even with digital TVs going forwards. Now, the key thing about the TV picture is actually made up of these lines, and it's made up by what's called a raster scan. And in general, what happens is that the electron beam coming from the electron gun at the back of the TV tube here, so this is the electron gun for the TV. There's generally a very high voltage, probably 20,000 volts plus, between the cathode here and the anode of the screen here. And this means that the electrons get fired at the screen, and these deflection coils here will actually scan the electron beam across the screen. The horizontal refresh frequency is used to handle the scanning horizontally across the screen, and the vertical refresh will then actually progressively move the electron beam down the screen until it gets to the vertical retrace period, when it will fly straight back to the top. Effectively, the raster scan system is moving the electron beam across the screen, and it is actually on a slight incline, in fact, as it goes across the screen here, although it's not really noticeable. And then the retrace periods are when the electron beam has to be returned back to the beginning of the line, or at the end of the frame it has to return to the top of the page. Now, the key thing is here is, with all of the inductance and things like that on these coils, then there is an amount of time that you need for this retrace period. Now, modern LCD monitors and things don't require this at all, but they still maintain backward compatibility because of these standards. Now, in the previous video, I did include a link that explained how cathode ray monitors work. So this actually explains a little bit more about it. And you can see here we've got the anode, which has got the phosphorus on the screen. So when the electrons hit the screen, then it glows. And generally, because the glowing is persistent for a certain amount of time, then our eyes just don't see the flickering very much. And you can see that all of the control circuitry, we've got the high voltage to provide the acceleration to fire the electrons actually at the screen there. And there's various things too. The gun control turns the electron beams on and off for the different colours. Grid control handles some of the focusing and the finer acceleration. And then the deflection coils handle the horizontal and vertical aspects of scanning the electron gun across the display. When we're doing computer video output, we need to make sure that the horizontal and vertical synchronization frequencies are correct, so that the video hardware is actually able to generate the necessary signals to produce our display. And you'll see here that it's showing the waveform that's generated. So you'll see these sort of sawtooth type waveforms, and you'll have a sawtooth waveform going down the vertical refresh, and you'll also have a much higher frequency horizontal waveform going across the page there. So key thing about this is making sure we've got the right vertical and horizontal frequencies, and also the key thing there in computer monitors is the dot clock. So this is the pixel clock that we use to turn the dots on and off. Now, this has actually come from the IBM 5153 CGA monitor schematics. So there is actually a PDF, Sam's Computer Facts, that actually provides all the schematic diagrams for the original CGA monitor. And in fact, when we scroll down here a little bit, you can see here we've got the vertical and horizontal drive circuits for the coils here. You can see the various outputs here. And in fact, you'll also see that this document includes a lot of the oscilloscope waveforms at various points on the circuit. And in fact, what I've done is, rather than having to go through that, what you can see here is that the vertical sync has this sort of sawtooth waveform, and you can see that the scale of this is on the scale of milliseconds. So in general, there are 60 hertz, 50 hertz sort of refresh rates. That's 60 or 50 frames per second. We're normally talking about 16 to 20 milliseconds per frame. Because the vertical sync signal here is causing the electron beam to go from the top to the bottom over a whole frame, but in fact during the period as it's scanning across, then in fact it will go down slightly. And you'll see here we get about 18.4 milliseconds visible time during one of these frames, and the retrace generally takes about 1.6 milliseconds. But on the horizontal side of things, horizontal sync here is about 15 kilohertz, and this means that each line is about 64 microseconds, so a lot smaller than the 20 milliseconds or 16 milliseconds above. The visible period is about 52 microseconds, and there's about 12 microseconds for the retrace period, which is about 20%. But the retrace is really limited by the coil inductance and the driving circuit, so there were sort of physics really limiting how quickly you could actually return the electron beam back to the beginning of the line or the top of the frame. But obviously now that we're using modern LCD and video capture hardware, they're not susceptible to these sorts of issues, but everything's backwardly compatible, so that's where some of these things have come from, particularly when we start talking about things like front porch and back porch. Are all to do with the timings, to do with these electron beams flying around the CRT display. So here's one of the diagrams from the original CGA technical documentation. We use this in the previous video just to explain some of the differences that we were doing on this Breadboard PC version. So the original cathode ray tube controller chip, the Motorola 6845, is a Hitachi version of this, which is able to run a bit faster, so it can run at frequencies capable of doing VGA refresh frequencies. It also has a couple of extra features to delay some of the signals. The display enable and cursor signals can be delayed by 1 or 2 character clock cycles. The timing generator control, we're going to be running at 25.175 megahertz, which is the basic VGA dot clock frequency. And that means we're generally going to be using 640 pixels across and 400 lines at 70 hertz. That's generally what the text modes in VGA run at. And we're not bothering with the composite color generation, so this is to produce the composite color needed to drive color TVs and composite output on monitors. But because we're going to be using a more modern VGA video output digital analog converter, that's actually going to take our digital color information and produce the necessary voltages needed for more modern VGA compatible monitors. So I'm not going to be dealing too much with the graphics because we're going to be handling the graphics later in the series. So I'm going to be looking more at the character-based side of things. So some of the key things you need to worry about here, that the original CGA design has these address buffers stroke latches. So we have the processor addresses and the addresses generated by the cathode ray tube controller chip go to the RAM. Now the RAM was a bit more complicated than the original CGA design because it was using dynamic RAM. This had to be refreshed as well as being used to access for the display and the processor. Because we're using static RAM, then some of that aspect is simplified, and so we won't worry too much about the refresh logic. Now the data latches here can be quite confusing, and what I have done here is these 2 data latches are also used for the graphics output, but I've actually labelled these the character latch and the attribute latch. And the key thing that these do is that when we're actually doing text mode on CGA, then in fact each character on the screen has 2 bytes. 1 byte holds the character value itself, which we get out of the character generator ROM, and the other byte handles the attributes for things like whether it's blinking, foreground and background colour, that type of thing. Now in fact on this diagram it doesn't really show it. The video output stage that determines foreground, background colours and things makes use of the attribute latch. So I've added this red line on here to show that in order to work out in text mode what we want to show, what it actually does, it takes a raster pattern from the character generator ROM. So this has the bits for each of the characters arranged line by line. And the alpha serializer, this basically takes those individual bits, 8 bits wide, and will actually convert those into a serial stream of 1s and 0s to determine whether we have the foreground or background colour. And this is using a shift register, and I'll go into that into a bit of detail. Now the key thing that the cathode ray tube controller chip here does is not only generate the addresses to scan the memory, it also produces the video synchronization. So you'll see here the video horizontal synchronization and vertical synchronization signals are just known here as horizontal and vertical. So that's one of the key things that this cathode ray tube controller chip is actually responsible for doing, generating these signals and timings. Then what we have to do in our clock generation circuit is actually generate all the necessary signals to control the latches here, control the shift register here, determine when the data's ready in the RAM here and when we can load it in here. And we have to do this quite quickly in a coordinated way so that the character ROM can be finding the right character before we serialize it. So these things have to go in a sequence. And in fact, one of the reasons why we've got some delays here, and we also have to delay the horizontal sync and vertical sync signals, is because there is a pipeline here. So it does take a couple of clock cycles for data to get here and to arrive out here. And if we don't include some delays in some of these other signals, then what in fact happens is we miss one or two characters. And we'll see that during the videos, that when we don't have these things right, then we may miss half or a full character in some cases. So what I'm going to do here is I've got various schematic diagrams open. There is a KiCad diagram for the original CGA video card. So this, I think I included the links in the previous video. So this has actually taken the schematics we'll be looking at and converted them into KiCad. And it's pretty much like for like. So it has dynamic RAM and all that sort of stuff. So this is something that if you can't read the schematics that easily out of the original documentation, possible to go back to this one. I've also got the schematic here for our version 2 CGA video controller, but because this is using a much larger complex programmable logic device, then a lot of the nuances of how these various bits fit together are all buried in this chip. And at the moment I'm just waiting for the 1508 chip to arrive, in that I managed to run out of the number of macro cells. 64 wasn't quite enough to actually do all of this, so I'm getting a 128 macro cell chip. Should arrive in the next day or two. But it's probably easier when talking about the Breadboard PC design to actually look at the version 1 video controller, because this design actually uses more discrete logic from these complex programmable logic devices. So let's take a look at the first diagram. So one of the things about the original IBM schematics in here is they tend to show you which sheet a signal is coming from on the left hand side here, and which sheet it's going to on the right hand side. So you'll see, if we zoom into some of these things here, you can see that some of these things are coming in from sheet 3, sheet 2, sheet 5, and where they're going off to. So when you're reading these diagrams, this allows you to see where things are coming from. So what this first sheet here, sheet 1 of 6, this has the cathode ray tube controller chip. So this is the Motorola 6845 chip. And then we've got the address bus coming from the CPU coming into these latches, which are effectively acting as multiplexers. And there's also the CRTC memory address lines coming out of here, which are then also being used to access the video RAM. And the key thing is here, because we're using dynamic RAM, then in fact this had to be latched in this particular way, because the video RAM had row address and column address strobes, and so we'd only actually give the address line sort of half at a time. So we do the columns and the rows separately, and that's the reason why these two latches had to be available here. There's also a bit of logic down here for doing with the graphics and the text alpha mode, in that in the graphics mode, then the graphics used the row address line coming out of the CRTC here. So the row addresses basically says which row the character is showing. And in fact, in the design that we're using, because we need to increase the 200 lines per screen to 400, rather than using 0, row address 0, we use row address 1. That effectively means each line is doubled up on the screen. And at the top here, there's some of the logic to do with the text mode controlling blinking characters, cursor, and generating the alpha dots output, which is actually used then to feed into some of the color generation circuits. So I'm going to go into the CRTC in a little more detail and explain how that all works. So 6845 is used by quite a lot of computers. Some of the later Commodore PETs used it, the BBC Micro used it, and also the monochrome display adapter and the color graphics adapter used the 6845. There was another similar chip in the Dragon 32 and Tandy Color computers, 6847. This had a lot more built into it, but it wasn't quite as flexible, and I think this is one of the reasons why some of these computers weren't quite as popular, because the graphics weren't quite as flexible as these other ones. Can address up to 16,000 characters, and the row address lines here, so the row address 0 to 4, allows us to build characters with up to 32 rows, although generally we only use 8 or 16 in general. It is designed for character-based applications, but as you'll see in the CGA card, it can be used for graphics, although you do have to do a few little workarounds. Now, because we're using the Hitachi device, this can actually work at faster frequencies. The original device wasn't able to work at 3 MHz plus character clock frequencies, is what we need for VGA, whereas this one can in fact do that. The horizontal sync and vertical sync signals which this generates, so HS and VS, sometimes you have to invert those for certain video modes, and we won't worry about the light pen. So there's a light pen here. Again, light pens won't generally work on LCD monitors, only on cathode ray tubes. So the CRTC chip is configured by up to 19 registers. So this only occupies 2 addresses in the I/O address map. And so what we have to do is to write the register address to register select 0, and then we write the data to register select 1. So 19 registers, and all these need to be configured correctly to get the right timing signals out of there, and I'll be covering that in more detail. Now, in general, for the text mode, we need about 70 Hz refresh rate, and with VGA compatible output, we need 1 pixel row 31,500 times a second. So about every 31 microseconds, we have to output a row of dots. Now, this explanation here, which is what I referred to previously, this is the tutorial on how the cathode ray tube works itself and how the various electron guns and coils scan the electron beam across the display. There's also this CRTC register timing site. This actually will help to generate a starting point for these timings. I found that there are 1 or 2 things on here which I've needed to change, but it does give you a good starting point. So if you were to put in the 25.175 here, and we generally want to have 16 rows per character for VGA, this will actually give you a good starting point for a lot of the register values, and I'll be showing you the register values I've used and what the original IBM BIOS had, and that actually helps to get the starting values close enough. You have to tweak them quite often to actually get it working exactly with the video hardware you have. The cursor controls when you get the cursor in text mode, normally an underscore underneath the characters, or it can be a whole flashing block. Display enable turns off the video output during the retrace periods, both horizontal and vertical. Now, the address outputs here don't get mapped directly to the video RAM address outputs, in that the MA0 output actually goes to the video address 1. And the reason for that is that we need to switch between the character value and the attribute value in text mode, and so we use a character clock value to switch VA0 from the character and attribute. Let's take a look at the datasheet for the CRTC controller. So this is the Motorola one. Now, it is worthwhile going through this to understand how this works. So I've sort of mentioned what the various pins and things are, and this shows a sort of a typical design of what you might build for this output. So you'll see that we've got latches running the character generator, ROM and shift register. This is for a mono output, so we haven't got any color here, which is why it's a little bit simpler. You'll see here that the clock frequency maximum is 3 MHz, and in fact we need 3.1 MHz or higher for VGA, so this chip by default wouldn't necessarily be able to handle the frequencies needed for VGA. And this chip is able to do non-interlaced displays, which is what we'll be using, and also interlaced displays. So in general, TVs tend to use interlaced displays, so we'd only display half the scan lines during alternate frames. You can see here that this shows how the characters actually output. CRTC will output the row addresses based on the definitions in the various registers, and you can see that when we then actually output the values here through a shift register, then the first scan line will obviously show the 3 dots there and then the 4 dots there. Then when it gets to the second line, then you'll see that we've got the dot there, and the dot there and the dot there. So this is how the raster image is actually built up. There's a detailed information on what all the various signals cover here and what all the registers are. And the key thing here is there are some limitations on the size of some of the register values. So in particular, the number of vertical total lines is a maximum of about 127. And this is one of the issues that when we want to use this for graphics, then 127 lines generally isn't enough doing graphics. And when we come to look at the graphics mode later on in the series, then we'll discuss how we can actually do that. And you can see here that the CRTC outputs rows of characters, and it will also output each line, will output the row address for each line. So we would actually get, say with 8 rows per character, we'd actually get the same character line being output 8 times, once for each of those lines, and it would move on to the next line. And you can see that for each horizontal line, there's a bit over here where we haven't got anything being displayed. So this is where the horizontal synchronization and the front porch, back porch periods will be, and they're allowing the electron beam to whiz back to the beginning of the line and start over again. And similarly, the vertical retrace period at the bottom of the display area, this is where it allows the electron beam to whiz back up to the top here. So in configuring the register values, you need to make sure that all of these things are compatible with the video monitors that we're using. If you get them wrong, generally won't cause too much damage to LCDs and video capture hardware, but if you're plugging this into a real monitor, you'd really want to make sure the signals were correct before you do this. So then it explains what each of the registers are, explains a lot of the timing. Now this can be quite confusing, but basically it's sort of showing for the non-interlaced mode how the picture is built up. And you can see here that if we have over here non-interlaced and then the various non-interlaced, where the lines we made up in alternate frames. Then for the cursor can actually, we control with the 2 register values what the start and end line for the cursor is. So if we made it the same, so 9, then in fact you just have a single bar. In fact, you'll see in our configuration we've probably got about 3 lines for the cursor. And if you really wanted to, if you had the start at 0 and the end at, say, 8 or 16 or something like that, then you'd have a whole block. We won't worry about the light pen. Now, in all of the calculations here, you'll see that the various register values are represented by these values here. And the only thing you need to be aware of is that some of the register values here, when you're doing the calculations, you have to add 1 onto it. So quite often the horizontal total and the vertical total, for example, will in actual fact have an extra 1 added to them. And this shows how the memory address values change as the various other signals change, and in particular how things change during the retrace. But we generally don't need to worry about this too much. As long as you've actually got the video RAM configured properly, then we shouldn't really need to worry too much about these sort of aspects of it. Now the calculations here tells you exactly how to, based on the dot clock and various other horizontal sync, vertical refresh, will actually show you how to calculate these things. The website I showed you will do the majority of that. It's not 100% accurate, but it's pretty good. But working through this lot manually is quite a bind, and I haven't put this into a spreadsheet, or I haven't put the calculations into a spreadsheet. And it's showing a run through how to do this. However, this particular mode, I think it's doing a 32 by 16 display, which would be a very old style display. The 80 by 24 is obviously more typical of a terminal, although 80 by 25 is what most PCs use. This shows how to calculate all these values. And there's even a blank sheet there. And here is some code that I think is in 6800 compatible code for initializing the CRTC. Now, that's the default one, but in fact, what this Hitachi device allows us to do is a little bit more flexible. The version I've got here is in fact capable of doing 3.7 megahertz clock speed, so it's able to probably do a higher resolution even than VGA. And it also actually includes a couple of enhancements. So there's the skew control, so this delays some of the display enable and the cursor signals, so this is configurable. And by default, the original 6845 for the vertical sync period would be 16 hard-coded, whereas this one actually includes the configuration. You can actually configure how many lines you want for the vertical sync rather than 16. If you don't configure it, it defaults with 0 in the configuration. It defaults to 16, which is what the 6845 has, but there are some extra features in here, so it actually builds on the 6845 and adds some extra features. And in fact, you can see here on the sync width here, there is a horizontal synchronization width, which is the same as the 6845, but there's then also the vertical width is also specified here. Now, if this is 0, it defaults to 16, but it is possible to override this. And then you can also see that the cursor and display enable skew have two parameters here to control the delay on those signals. And this explains the vertical sync width. If it's 0, we get 16 lines, and then these other values just give us 1 to 15 lines. Similar diagram to what we had in the original 6845. And when I show you the spreadsheet with all the various values, you'll see how these things sort of go to make the video timing. This again showing the cursor control, very similar to what I discussed previously. This does actually include a number of samples of how to actually use the chip. Complicated examples. Discussion about the parameters and the timing. And you might want to do something with color. How to have a cluster, CRT controllers, some samples here, and you can see then even some sample schematics. So the Hitachi document is a bit more detailed. This copy isn't great quality, but it's the best one I've been able to find. And then this actually compares the two versions. So the S version is the one I'm using and is the better version. So certainly if you can get this version, it does the 3.7 megahertz and also includes, in addition to some differences in the handling of interlaced video, has the vertical sync width, has the skew function, and is also able to work at these faster frequencies. So that's the CRTC chip. And what I have also done is a spreadsheet here which has got all of the values. So what I've done here is I've got all the various parameters. So we've got the dot clock frequency, so it's the pixel frequency, the horizontal frequency, which is really defined by the monitor, what it's capable of doing. Vertical frequency is generally going to be 50, 60 or 70 hertz, sometimes about 72. And then these other things are then needed to base around that. So the character clock is the clock which goes into the CRTC. How many pixels each character is made up of. Now, the original monochrome display adapter used 9 pixels across, I think because the IBM people wanted to have the characters looking as good for business use as possible. In general, although the VGA will also do 9 pixels across, I makes things a little bit more tricky, and so I tend to stick with 8 pixels. You'll see that MDA had 14 rows per character, whereas when you actually look at the CGA, it only had 8 lines, so the MDA characters looked a lot prettier. And in fact, the display resolution was in fact 720 pixels by 350 lines for the MDA, although this was interlaced, whereas for CGA, we've only got 640 pixels across and 200 lines. So these down here are all the various register values for the horizontal total. These are all in hexadecimal because that's what generally the things are specified in all of the configuration files. And you'll see here that the interlace mode, that in all of these early ones, these are all using interlace mode because we're generally going to be talking to TVs through RF modulators, whereas in fact the Breadboard PC ones, then in fact I'm not using interlaced mode, and in fact these extra bit values in here are in fact to do with some of the other configuration for the skew of the cursor and the display enable. One of the confusing things is the max scan lines shows how many lines each character is -1. So when calculating this, if you want 16 lines, then you need to set it to 0F. If you want 8 lines, you need to set it to 7. In fact, if you want to set it to 14 lines, you need to set it to D, which is 13. And this also shows where the cursor starts and finishes. So for example, where we're using 16 lines, you've got 0D to 0F is the cursor start and finish. That's 3 lines underneath the characters. So the key thing we need to look at first of all is what dot clock we use. So the dot clock determines how many pixels we can fit in across the screen. That's very much dependent on the frequency that the monitor can work at. And you'll see that in the early CGA, the 40 column text mode, which is really as much as you could use with a TV and an RF modulator, that the dot clock was actually half the speed as the 80 column mode. So you'd struggle to get any recognizable output with 80 column text on a TV, but you would actually be able to see in the 40 column mode here. But when we look at the Breadboard PC, in the version 1 of the series, I did a monochrome display adapter card, and this used the 25 MHz dot clock, which is the same as VGA. It also used the 31.5 kHz horizontal frequency, and you'll see that's almost twice as much as the other two. The MDA had an 18 kHz horizontal frequency, so you'll see that if you tried to plug a CGA monitor into MDA, then it probably wouldn't work and might even damage it because of the different frequencies here. And in fact, when running on text mode, then quite often VGA is actually running at 70 Hz, not at 60 Hz. And you'll see along here, apart from the 40 column mode, then generally the character clock here is 3.1 MHz. You can see that we're generally dealing with 8 pixels across width, apart from the original MDA, which was 9. Now you'll also see that the character height is quite often defined as 16. Now in fact, the characters in CGA are 8 by 8, but we double the lines up. So rather than having 200 lines, we double them up to 400. So by ignoring the RA0 line and only using RA1, effectively we double each line up. So in fact, although the ROM only has 8 lines per character, when they come out on screen they take up 16 lines because we're using the VGA output. And down the bottom here, what I have done is based on the various parameters up here, so the total number of characters on a whole line, how many of those are displayed. So you'll see 50 is 80. You'll see that then you can calculate what the horizontal frequency should be based on the dot clock, the character clock, and these parameters, and also how many vertical lines will be displayed, and then what the corresponding vertical frequency will be. So it kind of just gives a bit of a sanity check on these. But these values here came from Sergey Kiselev's BIOS, and I believe the same as what were in the original IBM PC BIOS. And these are the ones I've been using in my video series because we're using this faster dot clock. And then, although I haven't done any VGA 640 by 480 output actually so far in the Breadboard PC series, the Lunar Lander game I did in the original 6809 project did actually use 640 by 480 graphics, and these are the values that I actually had for that. And there are slight differences in things where the synchronization position is, the horizontal sync position. You'll see that there are differences between the different modes and things, and it's just a matter of a bit of trial and error to find out what works best with your particular video hardware. So that's your cathode ray tube controller. So it's primarily responsible for producing vertical sync, horizontal sync, changing the address lines to access the video RAM, and also providing the row address lines to show which line of the character we're actually outputting. And then there's just the CPU interface for the data lines, for the register select, The E is the Motorola compatible timing signal, which can be constructed from the IBM PC IO read, IO write, and the read write control. This clock here is the character clock, which we need to feed in, which will be about 3.1 megahertz. Okay, so the previous schematic, we had the CRTC and the video RAM. And what this is actually just showing is probably the more complicated bit of the design. What it's actually showing is that we've got the data coming out of the video RAM here, and we have the attribute latch and the character latch. So the character latch is taking the character code, feeding it into the character generator ROM here. And then we've also got the row address 0 to row address 2 coming in here. That's going to go from 0 to 7. And this is used to drive the lower 3 address bits of the character generator ROM. This means that when the font is loaded in the character generator ROM, we need to make sure that the row 0 is the top of the character and row 7 is the bottom of the character. And what this will then do is, as these values cycle through row 0, 1, 2, 3 up to 7, then we'll get the lines of the character. Each line of that character then goes into this shift register. The shift register is controlled by a load signal, which is generated by a clock circuit, which is normally known as the shift register latch. There is a clear signal that actually at the end of each character clears the values, and then the load signal actually takes these bits here, loads it into here, and then as the dot clock clocks this, we then get the bits coming out of here. This bit tells us whether we've got a 1 or a 0 on our character as we go across the screen. There's also a status register here, which is used by the PC to determine if we're currently outputting data. The attribute latch actually goes over to later stages to work out what sort of colour and foreground, background colours we're going to be using. We don't need to worry about the graphics side of things here. And this colour register also provides the background colours in some of the graphics modes and provides other sort of colour attributes, mainly for the graphics modes. And you will see here that sometimes this is sheet 2, sometimes you'll have sheet 2 here. So effectively this signal comes here and goes back down to here. And these colour encoder values here, so you see these things in orange here, these control whether we're actually going to be outputting the foreground text, background text, or whether in the graphics modes, what sort of colours we're outputting here. So in fact, the attribute latch here has the foreground and background values. We'll choose the foreground and background values based on these values here. It's worthwhile noting that the latch clocks and rising edges. So a lot of latches are actually triggered on a rising edge. So if you want something triggered at the start of a pulse, then the rising edge is this one here. So you'll see that, in fact, for the 574 latch and the 646 latches that we use, these work on rising edges. The 573 basically outputs the value as is when it is high, and then when the value goes low, then in fact it saves the value that was last going out of there. So this is used sometimes for address lines. This one generally is used in the video output circuitry because you want to make sure you're only latching something at a particular point in time. And if you wanted something triggered at the end of the pulse, then if you invert it, then in fact, if you have a value that gives you a sort of a positive value when you want to do something, if you want it actually triggered at the end of that pulse, you invert it, then you get a rising edge there. And this just shows the raster fonts. So we've got the row address RA0 to RA4 possible. Generally only use RA0 to RA2 or 3 to give us 8 or 16 lines. And you can see here this is the Frapped font editor utility. You can see here we've got two fonts. One is the wide font. You can see there's 2 pixels for each character. It's an 8 by 8 cell, and you can see we've got 256 characters there. And then if we go to the other one here, which is the thin one, you'll see that there's only 1 pixel for each of these. What the row address does is show this first row, then when it's done all those characters on the line, it goes back and does the same characters again and says show me line 1, then goes back and does the whole row again, show me line 2, and until it's done the whole lot, and then it goes on to the next character row. So this bit has the timing generator control. Now, because of the dynamic RAM and because of the differences for the VGA timing, then I'm not going to go through that in any great detail. There is a certain amount of address decoding for the video RAM, the I/O ports that we're using, and there is also a little bit over here in that the clocks which are used for the blinking of the cursor and the blinking of the characters is actually derived from the video sync frequency here. This is largely the dynamic RAM timing, so you can ignore that, but there is the control port here. Control port actually controls things like the video mode and whether or not we've got 40 character mode or 80 character mode or these higher resolution graphics modes. So sheet 5 here shows where the composite color generator is. So this was necessary to generate the NTSC or PAL type video signals. I suspect there may need to have been some differences for European CGA adapters, but because we're actually taking the digital outputs from here, so we're taking sort of red, green, blue and intensity values, and we're going to be feeding that into a video digital analog converter, which is VGA compatible, then we don't need to worry about this side of things. This is quite tricky to generate the necessary signals for producing the color. And you can see here that the output from the previous of red, green, blue and intensity pretty much just gets passed straight through for the CGA monitor output. This was only used for the composite video over here. Then finally, there's the composite video output we don't have to worry about. The light pen we're not worrying about. This is the ISA bus connector to plug into the rest of the PC bus. And you'll see here we've got a CPU data bus bidirectional buffer here and some logic to control that. That basically is the CGA design. There's a few other things we perhaps need to cover. So probably the most complex part of building a video card here is the clock timing and the various latch clocks. What I'll try to do here is just summarize this. I will dip into the schematic to actually show what I mean here. So the key thing really is what dot clock we use. Now the original PC used 14.3 megahertz. This is 4 times the NTSC color subcarrier frequency. But in fact we're using 25.175 megahertz, which is the lowest VGA compatible clock signal. And that really defines the pixel width, pixel size, and the capabilities for how many pixels per line we can show. Then we've got the character clock. Now we'll be dividing this by 8. So 25 megahertz divided by 8 is about 3.1 megahertz. That gives us 80 columns. In the original IBM VGA, there was also a higher clock rate, about 28 megahertz, which is actually would allow us to do 9 pixels with the same horizontal timing. So if you want to do 9 pixel wide characters, you have to have a 28 megahertz clock. Now within the design, you'll see that I'll mention QA, QB, QC, QD quite a lot. And all this means is it's taking the dot clock, QA is divided by 2, divided by 4, divided by 8, and divided by 16. So in fact, we're normally only using QA, QB, QC for 80 column modes. But when we're looking at 40 column mode, we tend to use B, C, and D. So the dot clock frequency is effectively 12.5 megahertz. So the characters are 8 pixels wide, so we're ignoring the 9 wide for Breadboard PC. And this drives the CRTC timing for reading the video RAM, generating the horizontal sync and vertical sync timing. And also we use this to switch between the character byte and the attribute byte. So the video address 0, the lowest bit value of the video address, actually uses the character clock here. So it switches between 0 and 1 for every character, and so this allows us to switch between the character byte and the attribute byte. Now to coordinate with that, we also need to make sure that the character latch clock loads the video RAM into the character latch to read the character generator EPROM raster lines. So effectively the character value provides the address lines for the character ROM. And then the shift register attribute latch clock, this loads the video RAM data into the attribute latch, so we've got the color information available. And it also, at the same time, will load the character raster output from the ROM here into the shift register. So if you just have a look at the shift register, this is the shift register we use, and basically what happens is once we load the values into A, B, C, D, E, F, G, so we use the shift load for that. So when that goes low, then it loads the pixel data from the character ROM in there. And then when the clock, which is driven by the dot clock, then shifts the input out through the QH output. And so that's effectively the output of the pixel data to feed into foreground, background logic. As we said, the register values here generate the horizontal sync frequency, and the register values there generate the vertical sync frequency. And the final thing we need to look at is, because we're not using a CGA monitor which has digital inputs, we're using a VGA monitor that uses values from 0 volts to 0.7 volts for each of the red, green, blue values. And so for that, what we're using is a video digital analog converter. This IMS video DAC allows us to set up 256 values for the red, green, blue values, and then based on 0 to 255 coming in here, then it will actually output the red, green, blue values. So this allows us to have up to 6 bits for each colour. So this is what gives us a possible 262,000 colours, but we can only have 256 at a time. So this removes some of the complexities of working out resistor values and things to produce the voltages coming out of here, and means that we can actually program the colours actually in the video DAC registers here. So this is the Breadboard PC version 1 schematic. So over here we've got the video output connector. You'll notice that we need to have 75 ohm values here because we have to make sure that the impedance or resistance is matched to the monitor. There's a constant current source here which is needed by the video DAC to generate the voltages out of here. We've got the cathode ray tube controller down here. And out of this, the horizontal sync and vertical sync actually go into here, and this is where it divides these down for the blink clock for the characters and the cursor. We also feed it into here and then comes out of here delayed up to the 15-pin VGA connector up here. If we see the character clock here is coming out of our clock PLD here, and you'll see here that coming into this on pin 1 is our 25 MHz dot clock. Then we've also then got the QA, QB, QC, and there's a QD down there as well. And this is also generating the character latch, the attribute shift register latch, and the character stroke attribute value. So this switches between using the character byte and the attribute byte. This is modified slightly from the character clock, and that's actually used to drive the video here. So depending on the video mode, then this will actually drive video address line 0. We've then got our character latch here. So this takes the data from the video RAM. So the video RAM down the bottom here. So this is the data out of the video RAM. And it then feeds that into the higher address lines of our character generator ROM. And you'll also see that on the lower address lines here, we've actually got the row address lines. Now, we're using row address 1, 2, and 3 here, not 0, 1, and 2, because we want 2 lines to appear for every line. So this doubles up from 200 lines to 400 lines. And then the output from the ROM here, so the dot data as it's known, this is fed into the shift register. The shift register has the attribute latch, which controls when it loads the dot data in here. We have the dot clock coming in here, and then the output of it is our S dots, and then the S dots goes over to here, where then we determine then based on the attribute latch and various other things what colours we're going to be showing. We also have the blinking of the cursors, display enable and all sorts of other stuff. So a lot of the logic is quite complex in these PLDs here. What this basically does is replaces a lot of the discrete logic which actually appeared in the schematics that we've been looking at. So then out of here comes the P0 to P3 are the values effectively for the colour that we actually want to show. And then based on what those values are, this will then generate the red, green, blue values, as long as we've already configured the registers in here to tell the video DAC what colours we need to output for each of the input values here. So I'm going to be going through this in more detail. So as we do the new version, as we do this version, as I go through it, I'll explain how the video sync, horizontal sync, and various other things are going as we go along here. But obviously, because so many of the rules are actually built into this complex PLD here, then there isn't so much to actually see. It's all done in the rules here. As I said, the only issue I've run into is this ATF1504 I'm using has 64 macro cells, and in fact I've used all of them up. I'm just waiting for the 128 macro cell version to arrive, and so hopefully that will allow me to do the next video in the next week or so. So thanks for watching. If you don't want to miss out on future videos, please hit subscribe, and if you hit like if you found the content useful, just helps to make the videos available to more people.